So my name is Ziye. It is my great honor to present this topic in Ceph Alcom virtual conference this year. So I think my presentation can be divided into the following four parts. The first will be the background and the problem, and secondly, we will introduce our proposed solution, that is to leverage hardware-based offloading technique to mitigate the CPU's bottleneck when operating persistent memory devices. And in the third part, we will introduce how to enable DSA. DSA's full name is Data Streaming Accelerator in Ceph. And finally, we will have the conclusion. So let's see the first part, background and problem. We know that with the trend, I mean that there will be more and more deployment of non-write memory devices. For example, Intel's Optane memory. Though I mean there are some strategy changes, but it will not change the trend. And the second is the CXL attached persistent memory. I think it will be available soon in the near future. So it means that with those devices deployed in data center, I mean that CPU resources on the host will become a bottleneck while operating on those persistent memory devices, especially, for example, with the application direct mode usage. It means that you can treat those devices which are attached in the DIMM as persistent storage. So it means that for this usage, it is different compared with operating PCIe SSDs or other SSDs. For example, I can use the diagram in the right part as the example. You can see in the left part, it is a hyper-converged infrastructure. It means that computing resources and the storage resources are deployed together. So you can see that when the system are attached with the PCIe or SSDs, when we run Ceph, the host CPU described, I'm fine to serve 20 virtual machines. Because my brothers, like the PCIe SSDs, they have the DMA ability to offload the read-write operations from the memory to those devices. So it means that CPU can have a bunch of plenty of CPU resources to execute virtual machines. But if you change this situation, it means that you replace those SSDs with the persistent memory devices. The CPU may complain that now I can only serve 15 virtual machines and are very busy because there is no DMA, direct memory access capability from those persistent memory devices. So it means that in such situation, without the DMA capability from the devices, CPU will be much busier to deal the read-write IOs to those devices. So we conclude that the root cause is that the data operations between memory or persistent memory is different from the data operations between memory and the devices. Because for the later usage case, there is DMA or RDMA capability on those devices. So there will not be too much burden on CPU resources. But when we use the persistent memory like devices, it will have more pressure on the CPU resources. So we think that how can we offload some work from CPU with some hardware offloading techniques. And we think this is a valid requirement, especially for those cloud providers in hyper-converged infrastructure usage mode. It means HCI mode. It means that the cloud providers would like to utilize the important CPU resources in the host to serve their customer visible workloads. For example, the virtual machines and the workload inside the virtual machines, instead of using more CPU cycles on persistent memory devices. Yeah. So it means that if we can save the CPU resources on the persistent memory, and there will be much more CPU resource remained to run more virtual machines, and those cloud hypervisors, they were happy to such usage. So I think this is a very common problem, and if we deploy many persistent memory devices in Ceph's OSD, for example, Brewster or C-store, we will face the same issue related with CPU utilization. So we proposed our solution. So we propose to leverage some memory offloading devices. For example, there are already some memory offloading devices provided by Intel. For example, Intel's IOAT, IO acceleration technology, and the upgraded version, Intel's DSA, data streaming accelerator. For example, data streaming accelerator is a high-performance data copy and transformation accelerator that will be available in Intel's next generation processors, for example, the Ceph Rapids, and it can be used to optimize streaming data movement or some other operations, and it can be used in many different scenarios in storage, networking, and also persistent memory. For example, the most popular operations can be the move operation. Move. It means that you can use the move to move data from persistent memory to memory or memory to memory. It can all be supported, and there can be other operations like the CRC operations or fill, compare, flash. And in this presentation, we will use the move operation and offload the memory and the movement from memory and the persistent memory. So I mean that there are still problems how to efficiently leverage those memory offloading devices. We think that we can have two different models to integrate those memory offloading devices, because there are already support from kernel or user library to integrate those devices. So it means that if we want to replace the memory copy operations or movement operations from memory and persistent memory, we can just replace the CPU statement with the operations dedicated by the library, and then we can use it. But the first usage is the sync mode. The sync mode is that you will not change the behavior of the application. For example, in Ceph's Brewster, you can just replace the operations provided by the PMDK library. It is very simple, and we know that the integration overhead is low, but the advantage will not be clear in CPU utilization, and the performance may not be improved for the workloads, because when you use the DSA to offload the operations, the programs still need to wait the result. So there will be no CPU side resource decreasing. And the second usage is async mode usage. The integration overhead is very high, because you need to rewrite the programs. For example, the very famous application work is the DBDK or SBDK, and in Ceph we now already conducted the C-store working, which is derived from C-star framework. It is also a async mode, but I mean that in Brewster, in the persistent memory devices library, currently I mean that if we want to change the async mode, there will be still additional work, and it is still in progress. So I mean that for this, integration overhead is high, but I mean that if we use this, there will be the CPU resource saving, and there will be definitely a performance improvement when we operate the persistent memory devices in Ceph's OSD. And to demonstrate that our idea is practical, we provided our solution in Ceph. Currently, I think that the sync mode to leverage DSA, I mean the code, is already in Ceph's master branch. And we use Intel's DML, data mover library, to drive DSA and firstly accelerate persistent memory operations in Ceph's Brewster. So this part we will introduce some details. I mean how to enable DSA in Ceph. So I mean that currently we divided our work into some steps. I mean that currently the mainstream work in Ceph is C-store, but I mean that the work is still in progress. So we will integrate the work in Brewster first, and then we will continue the work in C-store in the future. And in phase 1, we already have some achievement to offload persistent memories in Brewster, and we leverage Intel's data mover library or IDXT config library. IDXT config library is a tool to configure the DSA devices in the host if you have Intel's latest SPR platform. And even we enable the DSA configuration in Ceph with the configuration. If we do not configure the DSA devices in the host, it can still we can still run the Ceph with the software path provided by our approach. So I mean that it will not hurt the usage of Ceph if you configure the DSA enabling, but there are no DSA devices in the host. And the step 1 is to use the synchronized APIs in DML library to offload the CPU operations. And the expectation is the functionality can work, and we already achieved this. I remember the following two patches are already merged, maybe in the middle of this year, or maybe I mean that in April, or in April maybe, yeah. And the first patch is that we did some work to support the DV-DX usage on persistent memory, and in the next pages we will introduce why we want to this. And the second patch is that we just leverage the synchronized APIs in the DML library to operate on persistent memory, and we already did some evaluation in our own environment, and it works well. And the second step is that we propose to use a sync API in DML library to offload the CPU operations. And this work is still in progress. And firstly, we will rewrite the implementation details in Brewster's PMEM device implementation, and changes the sync behaviors on persistent memory with async. Then we will replace the CPU operations in async mode with offloading devices. And the expectation is that we should have the performance improvement and mitigate the CPU's pressure. But currently, I mean that according to Ceph's architecture on Brewster, I think this work will not be easy. It is different with the applications which use SPK application framework, because I mean that in SPK's async framework, we already enable the DSAs with some operations. For example, the CRC checksum in many over TCP workloads, and we already have the very huge performance improvement, which is already demonstrated in this year's Intel's innovation event. And we also have the POC code. It is not merged in SPK's master branch, but it is available on SPK's code review website, and it also demonstrates the performance improvement. Yeah. And we know that there are two possible usage on Intel's Optane devices in application direct mode. Application direct mode, it means that you can treat the persistent memory as the persistent device. It means that you write the data into this device, and you just shut down the machine, and the data will not be lost. So I think it is a very good feature. And when you configure the persistent memory with the AD mode, there still can be two modes to use this device. For example, the first usage is FSDX mode. It means that you format the persistent memory device with FSDX choice, and the users get block devices. For example, you can see a device named as /dv/pmemdevice.cc in the host, and the users can create a file system, especially kernel-supported file system upon that. And second is the DX mode usage. You format the persistent memory with DX choice, and you get child devices. For example, the /dv/dx0.0. But you can still direct operate on such devices and treat it as block devices. Yeah. And when you use the FSDX mode on persistent memory, you need to use the DX choice to mount a device. Then you can use PMEM library with CPU to obtain the persistent feature provided by the PMEM devices. Unfortunately, if you use DSA to offload the operations on persistent memory with such configuration, it will not always work. because it needs the support from a Linux kernel. So it means that if we want to have a general DSA enabling work in Ceph and not rely on the kernel, we need to address this issue. So we raised the PR, this PR 45609 half years ago, and with this PR. And this PR is already merged in Ceph's master. We can leverage persistent memory with DX mode directly. So with this mode, it can be very easy to use both CPU or DSA to conduct the operations on the persistent memory device, and it is equal, and you don't need to change your kernel. So we think that this PR is needed. So at that time, I mean that the maintainer Kefu, he just reviewed this PR and merged that. So let me introduce the DML library. So what is DML library? Intel's DML library is an open source library to provide the data manipulation on both CPUs and DSAs. It can leverage DSA's work queues exported by the kernel and offload the operations by CPUs. And when there are DSA devices available on the platform, you can use IDE config to create DSA work queues. And when DML library is used in the application, it will implicitly use DIOpen to open IDXT library and leverage created DSA work queues in hardware paths. And in Brewster's configuration doc page, we already share how to use IDE config to configure DSA working queues if you already enable yourself to offload persistent memory operations with DSA. So we already introduced our work with the sync mode support in Brewster, and the code is already available. And we still have the plan to enable DSA in async mode. And we summarize the work into the following 2 steps, as I described previously. First, we need to change the current usage mode in PMEM module, I mean the pmemdevice.cc file, to create a help thread like the approaches in kernel device or SBK ME device solution to conduct the operations on persistent memory by CPU in async mode. And at Intel, we have some colleagues is already on this task force. And the second is that then we will replace those async operations conducted by CPU by DSA. We will leverage the async APIs in DML library. Yeah. And phase 2, we want to still offload persistent memory or memory operations in C-store because C-store uses C-star framework, and we will expect a good async behavior in C-store. So we will do the following works when C-store is stable. For example, we would like to use DSA to offload some other memory-related operations. For example, the dual-cast, Corby, or CRC rated checksum operations. And we still want to use DSA to continue optimizing those operations on persistent memory in C-store or the CX attached memory with the sync behavior in the near future. So the conclusion is that let me just review what I presented today. We realize the overhead, bottleneck of CPU to conduct data operations between persistent memory or memories while performing storage workload. The main or the root cause is that the data operations between persistent memory are different from data operations between memory and device, because for the later case, there is RDMA or DMA capability on those devices, so there will not be too much pressure on the CPU, and especially when we deploy Ceph in hyper-converged infrastructure, if we equipped with the PCIe SSD, SAS or SATA SSDs, I think that the CPU will not be the the main bottleneck. But I mean that if you replace with the persistent memories, I think that you need to redeploy and recalculate the CPU resource to use. So it means that to address this problem, we propose to leverage the hardware-based offloading engines, for example, Intel's IOAT or DSA. But I mean that you can also use other offloading devices like the FPGAs. Yeah. And in my presentation today, we introduced the work to leverage DML Library to offload persistent memory by DSA in Ceph. We just introduced the work in Brewster with already completed work in Brewster and the ongoing work. I mean that to use the async libraries provided by DML and to change the PMEM device code in Brewster. And I mean the next step is that we will continue this work. We will continue improving the performance on persistent memory or CXC attached memory through those memory offloading engines based on DSA or the potential, the other offloading devices. I think for the performance report, we may publish it later after SPI is launched. You know that this machine is still not ready in the market. So I think that it's all my presentation today. Yeah. Thanks for your attention.